Rutherford's scattering experiment gave us the first glimpse into the atomic structure, but how does the Born series refine it at the quantum level? Today, we'll explore how these two game-changing concepts work together to reveal the deeper mechanics behind particle interactions. And in such, the Born series is used here to tell you how particles interact given some incoming wave. And we'll or incoming incoming wave, and we'll see how all this plays together. Very cool stuff, but we'll touch on that more later. The problem at hand today is problem 10.14, okay, in which we want to calculate theta as a function of the impact parameter for Rutherford scattering in the impulse approximation. This impulse approximation is the Born series, okay? And then we want to show that the results are consistent with the exact expression, which we found in 10.1a, in the appropriate limit. So a lot of back checking on this and making sure that the models are all working together. So why do we care? Well, as we kind of saw briefly in the diagram, it offers a systematic way to approximate solutions to the complex quantum scattering problems using a perturbation theory. Okay, but like with every other approximation method, we're going to have difficulties at some point. So the challenge for you is, what are the limitations of this method? We saw in things like the WKB, the kind of restrictions we had, variational principle, the restrictions we had, and of course perturbation theory, where the perturbation needed to be small relative to everything else. So although we have easy access to these methods, what is the limitation of this method? Okay, and this problem in particular had a lot of work to do, but most of it's in the video itself. But if you want the PDF, feel free to comment and I'll send you the link to the Patreon for it, and then you can have it for your savings or your library if you wish. If you're curious about the world of science, be sure to subscribe. I post educational content every week to quench your thirst for curiosity. With that, let's jump straight into this question. Okay, stop number one. We have to remember that in the Rutherford scattering case, we saw that we needed to accommodate the scattering of particles via the Coulombic force. And if we want to, let's recall what this diagram is, because as you see, we're going to need the perpendicular component. So in the scattering picture that we had for Rutherford, we had Q1 being on the ground, and we're trying to run it with Q2. And as we see, we get the scattering angle and then the force of the particle exhibiting on one another. But because we need the perpendicular component, F perpendicular is pointing up here instead of in the radial direction as we would expect. So because of this, we know we're going to need to use some clever geometry, in particular with phi. We're going to want the alternate interior angles here, and then we're going to mock everything up via this triangle. Okay, so the perpendicular component here to this horizontal line is going to be this b. Okay, so because we're going to need cosine and things like that from the force, we're going to have to reference this triangle a lot. Then r here is the distance between the 2 points, so keep this diagram in mind whenever you're ready to put into action what these things and these functions actually want. Okay, so from here, we can get the geometric quantities needed to evaluate the integral of 10.95 due to the perpendicular component, which is what we see here. And the perpendicular component of the Coulomb force is given to us by a cosine instead of having r hat. Okay, and now geometrically speaking, that cosine, the angle is touching the b side, which is the impact parameter. Okay, and then the hypotenuse was the r. So when we simplify this, we get that the perpendicular force is b over r cubed. Pretty cool. But r, being the distance between the 2 points, was also given to us, and we need to put this in terms of x and the impact parameter, mainly because we want impact parameters. Okay, and so because of this, we can use Pythagorean theorem and just tidy this up very quickly. Okay, we see that r squared equals x squared plus b squared from the triangle in the diagram. Pretty cool. Solving that for r, we just take the square root, put that as a 1/2. And then in the force equation, we see that we have an r cubed, so we just need to cube everything here. And in doing so, we see that we get x squared plus b squared to the 3s power. And now we're ready to put this into the integral equation and actually solve it. All right, cool. So Here we are with our integral equation, which, by the way, is equation 10.95, where we have the perpendicular part of the force and dt. Now, before we can do any of the evaluation, the last part for us to consider is that this integral, it has dt here, but what we need is that relate it to dx, okay? And the easiest way, which will help when dealing with the momentum later, is via the velocity. So since v is equal to dx over dt, dt is equal to dx over v. Okay, so all we did was separate that, all right? And then when we plug everything in, we see we get a host of constants here. All of these are constants, and this v is a constant. Okay, we shove the particle into the scattering experiment with some velocity that we know. So that doesn't change with position. We just have an incoming velocity, so it's a constant, and we're good to go. From there, then, what we observe is that we have from negative infinity to infinity with an integrand that's even. And because we're even or symmetric about these bounds, we can cut this in half and double it. And upon doing so, this will help save us time later. And this 2 we put into 1/2 form here, which looks a little janky right now, but trust me, when we come to it later, we'll be okay. And this is done on purpose. Not only that, but after we do that, we see that we have an x squared plus b squared in a square root situation. And so what we can use is our old friend trigonomic substitution. Okay, so here, since we have x squared plus b squared, we want the sub to be x equals b tangent. So then x squared equals b squared tangent theta, and dx is equal to b secant squared theta d theta. Okay, pretty straightforward substitution. The tricky part here is that when we're dealing with the changing of the limits, if x is at positive infinity and we know that tangent is sine over cosine, then we know that to get infinity, we need cosine to be 0, and that only happens when theta equals pi over 2 within the domain of the tangent function and arctangent function. Now, similarly, if we have our bottom limit, which is 0, that means that we need the numerator to be 0, and that only happens when theta equals 0. Okay, so we're good to go for our new limits, pi over 2 and 0. So with that, we can substitute that in and be on our merry way simplifying this integral. And now that we have it like this, we can factor out this b squared and get to work. Okay, so as we see, we factored out the b squared. Now we're left with tangent squared plus 1, but we can use Pythagorean identity, and that turns into a secant squared. And then here, if we put these two together, take the square on the outside like we do down here, that square and that 1/2, they cancel, and now we're good to go to simplify the rest of this integrand, which will actually come up pretty quick and pretty easy, all things considered. So now we cube every component in the denominator, and that cube cancels out everything in the numerator, leaving us with the b and secant down below, which is simplified here. Again, since b is a constant, we take it outside like we do here. And since secant itself is a reciprocal identity, which is 1 over cosine, since we're dividing by a fraction, we multiply by the reciprocal, and that gives us cosine as the integrand. So all that messy looking thing that we had before simplifies to something really sweet. Okay, and the antiderivative is sine, evaluated upper bound minus lower bound. This goes to 1, this goes to 0, so this whole bracket is 1. And then we're left with the integral expression here, which is pretty easy. Okay, now that we have the integral expression for the perpendicular force segment, we can plug this into the angle approximation, which is given by 10.96 in the next couple pages. So that really wasn't too bad of the setup from the geometry. So if you're finding this helpful, don't forget to give us a thumbs up. It helps more curious minds like you discover this content, and we can grow this community together. Which, by the way, if you saw the Nobel Prize, what did you think about that? I'm very curious. All right, so then we're on to stop number 2, where we can evaluate this integral expression now, or the result of the integral, into equation 10.96, where we can solve for the scattering angle theta. Okay, so that's the perpendicular component over the momentum, and this is why I said earlier that putting v in there early would help us. Okay, so p is equal to mv, and then we plug in the result here. And this is why I told you putting that 2 from doubling the integral for the symmetric part of it would help you because now you have 1/2 v up here and an mv here. We can combine those denominators to 1/2 mv squared. Okay, and that will put us with impact parameter b. But because 1/2 mv squared is the measure of energy, we can put that in, and that's what we're going to need with this impact parameter because we wanted to relate the impact parameter to E, especially in the Rutherford scattering case. And what this does is help us in comparing the results that we had previously. So that's a very keen insight there, and I hope the color code helps you with that. That being said, the impact parameter is given as tan inverse Q1 Q2 over 4 pi epsilon naught E times the impact parameter B, or we can solve it for tangent and be on our merry way and be good to go. So let's compare this with our first result from the first problem and see if they're the same. That brings us straight to stop number 3. Now, in order to compare this with the results from problem 10.1a, let's first solve for the impact parameter from this given result. Okay, that's why I did the tangent on the other side, or on the last slide. And we need to multiply the b over, divide by the tangent. And so we see that we solve for the impact parameter pretty quickly. But what we're trying to do in the comparison is to form match it and see what needs to actually be evaluated. So in the Rutherford scattering that we did in problem 10.1, we had an 8 down here. So we multiply this thing by 1, and the 1 takes the form of 2 over 2. That turns this 4 into an 8, and then we have a 2 on this cotangent. And what this allows us to do is that when we compare these two formulas, we see we get Q1, Q2, 8 pi epsilon naught E, and then the result we found from 10.1. So you see why we put the 2 over 2 there to make this 8 and 8 match. And then what we're left with is 2 cotangent theta and cotangent of theta over 2. This is what we need to actually compare. And let's get to doing that now. So from that, it is now evident that we must show that 2 cotangent theta equals cotangent of theta over 2 within this particular regime. Okay, so let's first recall what regime we were actually in for the impulse approximation or the Born series approximation. Surprise, surprise, this equates to the small angle approximation with respect to these functions. So for small angles, what we observe is that since 2 cotangent is equal to 2 times cosine over sine, the small angle approximation for cosine is 1. The small angle for theta or sine theta is just theta, so multiplying the 2 yields us with a 2 over theta. Similarly, we have cotangent of theta over 2, which gets split into cosine of theta over 2, sine theta over 2. And if we use small angle again, that cosine goes to 1, that sine goes to theta over 2, dividing by a fraction, multiply by the reciprocal, and I get 2 over theta. So indeed, these are the same value in the small angle approximation, and since they're the same values, we have the same approximation, and we're good to go. How awesome is that? We have all these different perspectives, and yet they're leading to equal physical results. And that's really darn cool to me, and very good to see that we're self-consistent. Very much a win-win situation here. Okay, so in summary, we got to see how the Born series worked a little bit. There's still a lot left to dig up, and if you like that opening picture, I will link it at least in the Patreon page and hopefully down below in the YouTube if it allows me to. Because what we saw in that propagation style form and the vertex form, that's what a lot of the diagrams that Feynman came up with started using a lot of in order to help us with these scattering problems. Okay, so QFT uses this concept quite a bit. But much like we saw in electrodynamics, and much like we're going to see in future classes with differential equations, Green's functions will not leave us alone, and they will come back with a mighty vengeance. So it is absolutely worth investigating how to find them and how to use them because they are very, 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 very useful. Okay, so with that, I ask that you please share this with all your friends who are curious about science, and let's grow this community together. I think we saw with the Nobel Prize how weird this community is now getting insofar as how diverse the perspectives can become in solving problems. AIs, the convolutional neural networks, things like that, very, very much what we want. and in StatMech, which we will get to hopefully by next year, that becomes a very key insight for us in doing large problems. I mean, have you ever thought about how many molecules are in the room with you? That's quite a bit, yet alone all their micro and macro state arrangements. Very weird. Okay, so very much on par for what we should be coming into in due time, but I'm glad to see that we're having these conversations now, especially on Reddit, X, and Instagram. There's been a lot of weird feedback with this Nobel Prize, in particular. But nonetheless, thank you again to all the supporters of this channel. You really do make this possible, especially with me running around like a headless chicken, thanks to two different hurricanes in the U.S., where we had Helene and now we had Milton in Florida. It's going to be a while before I can just get back to this more consistently. So I appreciate everyone's patience and just checking in, things like that. I hope that everyone's semester is going well, and I really do wish to thank all of our Patreon and book donors because we're going to do a lot of fun stuff come 2025, and I'm excited. That being said, books, notes, and other reference materials are found below. If you have any questions, please feel free to reach out. As always, thank you for watching, and until next time, stay curious.